Alright, then coming to system coupling. So in general, uh, you all know that Ansys has done a lot with multiphysics lately, and also with integrating different multiphysics type of solutions. So if you look at thermal and mechanical and CFD and acoustics, all these things, they're starting to become more and more tightly integrated. Now, if you look at the system coupling between structural mechanical and CFD, like Fluent, it has been around for quite a while, but now they have enhanced it as well with thermal behavior. So it's called coupled field static, both for so coupled field both for static and transient, and it just means that you can include thermal behavior as well, for example for conjugate heat transfer. And if you look here at the definitions, so from the thermal part we could now provide variables like the temperature, the heat flow, the heat transfer coefficients, the convection reference temperature, to transfer them to CFD. And for the structural variables, for example force and displacement, we can transfer them to CFD. And then I mean, as always, you have your right mouse function, and so if I click on the coupled field transient in the mechanical tree, you right click, you can insert, for example, different regions. So you can either insert structural or thermal region, and then if you define structural here, system coupling, you will get an automatic program control type of transfer of variables. But you can also dive into that as well, and you have more options there. So if you change it from program controlled to expert, then you have more options to select particular thermal and structural degrees of freedom that you want to transfer to CFD. But normally you would use the program controlled, I suppose. Okay, so there's an enhancement as well in the static to transient analysis for nonlinear problems. So when would you use that? Now, let's say if you have a very large model with rigid body motion, for instance. Let me show you the slide, the next one here. So here you got a very large model that would typically struggle to converge in a static solution because you have little gaps between bodies. You have a lot of different bodies, lots of frictional contacts, and all these contacts, if they have a numerical gap, it results in a rigid body motion. And you can imagine if you have that type of behavior, a static structural solver will struggle a bit because inverting the stiffness matrix is going to be tricky then. Same when you have buckling or any type of instability. Static solvers, they struggle. So a few versions ago, Ansys implemented the static to transient but used the explicit solver. Now the idea again was that if you go to a dynamic solver, solving instabilities and rigid body motion is a lot easier because you're not just inverting the stiffness matrix, but you have your mass matrix and often your damping matrix as well, which then allow the system to solve. The only problem with an explicit solver, it uses a very small time step. So explicit solvers are great for events like impact, explosion, drop tests, events that happen in a very short time, and you typically use a really small time step to solve it. But for a quasi-static type of solution, they are less suitable. So then Ansys implemented this static to transient switch with the implicit transient structural solution in Ansys. And that works actually quite well. So there's an automatic switch when you get instability, and that instability, as I said, could be caused by contacts or could be caused by some buckling. For instance, if you look at the movie on the right, we can see that this structure buckles, and then whilst buckling, eventually it will actually contact that plane on the right, and when it touches that plane, of course it stabilizes again, so then the dynamic solution can automatically switch back again to the static solution. So you just use the dynamic solution to basically get through your instability and then switch back automatically to the static solver again. So that can definitely help you with these type of problems. Okay, post-processing and graphics, a little bit about that. Yes, the animation has been enhanced. Again, this is very handy when you have very large models and you want to create animations, or if you have highly nonlinear or very heavy transient simulation with lots of time steps, big models. Animations, they can take a lot of time to generate, to use a lot of memory as well. And if you go to the options and go to the graphics display and select animation mode accelerated, which is a beta version at the moment, you get much faster behavior. It uses less memory, it's much faster, and you can even now animate and rotate, so rotate the model while it's animating. So you can zoom in, zoom out, rotate, translate the model while it's animating, and it's much quicker as well. And you can see that even the graphics is better if you look at that picture on the right. For the accelerated animation versus standard, the graphics is a lot better as well. So it's definitely improvement. Another thing in post-processing are the probes. So we all know that you can add probes to your deformed result, showing you in values what those results are. But when you have large deformation, for instance, if you have, let's say, a rubber boot that goes through large deformation, or you scale up your deformed result, then in the past those probes, they didn't move with the body, so that was a bit confusing. But now actually the probes, that text will move with the deformation, so that keeps it nice and consistent. And if you want, you can also change the color and the font size, etc. So there's just more options here. If you just want to make it clearer, or you just want to use some color for some text, you can do that here in the mechanical options, the graphics again.